Hi friends, this is N. Rakesh Reddy studying BTech first year in Johnson's Institute of Technology. Today we will discuss about nanoelectronics and its contribution to present day technology. Nanoelectronics refers to the use of nanotechnology in electronic components. The term covers a diverse set of devices and materials with the common characteristic that they are so small that interatomic interactions and quantum mechanical properties need to be studied extensively. Some of these candidates include hybrid molecular semiconductor, electronics, one-dimensional nanotubes, nanowires. Example: silicon nanowires or carbon nanotubes are advanced molecular electrons. Nanoelectronic devices have critical dimensions with a size range between 1 nm and 100 nm. Recent silicon MOSFET metal oxide semiconductor field effect transistor or MOS transistors technology generates are already within this game including 22 nanometers. CMOS complementary MOS nodes and succeeding 14 nm, 10 nm and 7 nm FinFET fin field effect transistor generators. Nanoelectronics is sometimes considered as disruptive technology because present candidates are significantly different from traditional transistors. Fundamental concepts. In 1965, Gordon Moore observed that silicon transistors were undergoing a continual process of scaling downward and observation, which was later codified as Moore's law. Since his observation transistors minimum feature sizes have decreased from 10 micrometers to the 10 to nm range as of 2019. Note that the technology doesn't directly represent the minimum feature size. The field of nanoelectronics aims to enable the continued realization of this law by using new methods and materials to build electronic devices with feature size on the nanoscale. Mechanical issues. The volume of an object decreases as a third power of its linear dimensions, but the surface area only decreases as its second power. This somewhat subtle and unavoidable principle has hug ramifications. For example, the power of a drill or any other machine is proportional to the volume, while the friction of the drill's bearings and gears is proportional to their surface area. For a normal sized drill, the power of the device is enough to handily overcome any friction. However, scaling its length down by a factor of 1000, for example, decreases its power by 10,003, a factor of a billion, while reducing the friction by only 1,002, a factor of only a million. Proportionally, it has 1000 times less power per unit friction than the original drill. If the original friction to power ratio was say 1%, that implies the smaller drill will have 10 times as much friction as power. The drill is useless. For this reason, while super miniature electronic integrated circuits are fully functional, the same technology cannot be used to make working mechanical devices behind the scales where frictional forces start to exceed the available power. So even though we have seen micro photographs of delicately attached silicon gears, such devices are currently little more than curiosities with limited real world applications. For example, in moving mirrors and shutters, surface tension increases in much the same way, thus magnifying the tendency for very small objects to stick together. This could possibly make any kind of microfactory impractical. Even if robotic arms and hands could be scaled down, anything they pick up will tend to be impossible to put down. The above being said, molecular evolution has resulted in working cilia, flagella, muscle fibers, and rotatory motors in aqueous environments, all on the nanoscale. These missions explained the increased frictional forces found at the micro or nanoscale. Unlike a paddle or a propeller which depends on normal frictional forces, the frictional forces perpendicular to the surface to achieve propulsion, cilia, development motion for the accelerated drag or laminar forces. Frictional forces parallel to the surface present at micro and nano dimensions to build meaningful missions. At the nanoscale, the relevant forces need to be considered. We are faced with the development and design of intrinsically pertinent mechanics rather than the simple reproductions of macroscopic ones. All scaling issues, therefore, need to be assessed thoroughly when evaluating nanotechnology for practical applications. Nano fabrication. For example, transistors which involve transistor operation based on the single electron. Nano electronic mechanical systems also fall under this category. Nano fabrication can be used to construct ultra-dense parallel arrays of nanowires as an alternative to synthesizing nanowires individually. Of particular prominence in this field, silicon nanowires are being increasingly studied towards diverse applications. In nanoelectronics, energy conversion and storage such sem2 can be fabricated by thermal oxidation in large quantities to yield nanowires with considerable thickness. Nanomaterial electrons, besides being small and allowing more transistors to be packed into a single chip, the uniform and symmetrical structure of nanowires and our nanotubes allows a higher electron mobility, faster electron movement in the material, a higher dielectric constant, faster frequency, and a symmetrically electron hole characteristic. Also, nanoparticles can be used as quantum dots, molecular electrons, single molecule devices are another possible. These schemes would make heavy use of molecular self assembly, designing the device components to construct a large structure or even a complete system on their own. They can be very useful for reconfigurable computing and may even completely replace present FPGA technology. Molecular electronics is a new technology which is still in this infancy but also brings hope for truly atomic scale electronic systems in the future. One of the more promising applications of molecular electrons was proposed by the IBM researcher A.R.I. Aviram and the theoretical chemist Mark Latter in their 1974 and 1988 papers. Moleculars for memory, logic and amplification. See unimolecular receiver. One of the many possible ways in which a molecular level diode might be synthesized organic chemical a model. Nanoelectronic devices current high technology production process are based on traditional top-down strategies where nanotechnology has already been introduced slightly. The critical length scale of integrated circuits is already at a nanoscale 5 nm and below. Regarding the gate length of transistor in CPUs or DRAM drives, nanoelectronics holds the promise of making computer processors more powerful than are possible with conventional semiconductor fabrications techniques. A number of approaches are currently being researched, including new forms of nanolithography, as well as the use of nanomaterials such as nanowires or small molecule in place of traditional CMOS components. Field effect transistors has been made using both semiconducting carbon nanotubes and with heterostructured semiconductor nanowires. SINWS. Memory storage. Electronic memory designs in the past have largely relied on the formation of transistors. However, research into crossbar switch based electronics have offered an alternate using reconfigurable interconnections between vertical and horizontal wiring arrays to create ultra high density memories. Two leaders in this area are Natro, which has developed a carbon nanotubes based crossbar memory called NanoRAM, and Hewlett Packard, which have proposed the use of mersed material as future replacement of flash memory. An example of such novel device is based on spintrons. The dependence of the resistance of a material due to the spin of the electrons on the electric external field is called magnetoresistance. This effect can be significantly amplified. GMR gained magnetoresistance for nano-sized objects. For example, when two ferromagnetic layers are separated by a non-magnetic layer, which is several nanomaterials thicker. The GMR effect has led to a strong increase in the data storage density of his disks and made the gigabit range possible. The so-called tunneling magnetoresistance is very similar to GMR and based on the spin dependent tunneling of electrons through adjacent ferromagnetic layers. Commercial production of nanoelectric memory began in the 2010s. In 2019, SK Hynix began mass production of 16 nm NAND. Flash memory and Samsung Electronics began production of 10 nm multi-level cell MLC and flash memory in 2017. TSMC began production of SRA memory using a 7 nm process. Novel optoelectronic devices. In the modern communication technology, traditional analog electronic devices are increasingly replaced by optical or optoelectric devices due to their enormous width and capacity respectively. Two promising examples are photonic crystals and quantum dots. Photonic crystals are materials with a periodic variations in the refractive index with a lattice constant that is of the wavelength of the light used. They offer a selectable band gap for the propagation of a certain wavelength, thus they resemble a semiconductor but for lighter photons instead of electrons. Quantum dots are nanoscale objects which can be used among many other things for the construction of lasers. The advantages of the quantum dots laser over the traditional semiconductor laser is that their emitted wavelength depends on the diameter of the dot. Quantum dot lasers are cheaper and offer a higher beam quality than conventional laser diodes. Quantum computers. Entirely new approaches for computing explore the laws of quantum mechanics for novel quantum computers, which enable the use of fast quantum algorithms. The quantum computer has quantum bit memory spaced on qubit for several combinations at the same time. This facility may improve the performance of the older systems. Radios. Nanoradios have been developed structured around carbon nanotubes. Energy production. Research is ongoing to use nanowires and other nano structured materials with the hope to create cheaper and more efficient solar cells that, and that are possible with conventional panel silicon solar cells. It is believed that the invention of more efficient solar energy would have a great effect on satisfying global energy needs. There is also research into energy production for devices that would operate in vivo called bio-nano generators. A bio-nano generator is a nanoscale electron-chemical device like a fuel cell or galvanic cell, but drawing power from blood glucose in a living body, much the same as how the body generates energy from food. To achieve the effect, an enzyme is used that is capable of stripping glucose of its electrons, freeing them for use in electronic devices. The average person's body could theoretically generate 10 watts of electricity, about 2000 food calories per day, using a bio-nano generator. However, it estimates is only true if all foods were converted to electricity and the human body needs some energy constantly, so possibly power generation is likely much lower. This electricity generated by such a device could power devices embedded in the body such as pacemakers or sugar-fed nano robots. Much of the research done on bio-nanogenerators is still experimental, with Panasonic's Nanotechnologies Research Laboratory among those at the forefront. Medical diagnostic. There is great interest in constructing nanoelectronic devices that could detect the concentrations of biomolecules in real time for use as medical diagnostic, thus falling into the category of nanomedical. A parallel line of research seeks to create nanoelectronic devices which could interact with single cell for use in basic biological research. These devices are called nanosensors, such maintained on nanoelectronic towards in vivo protection sensing should enable new applies for health monitoring, surveillance and defense technology. Thank you.